let's start the lecture by solving this nice and simple quiz. So, what do I need to calculate? I need to calculate, as the first thing, the force vector acting on each particle. What was our Lorentz force? F was Q V cross B. Now, I have two particles here, plus Q and minus 2Q, right? So let's try to find the direction. Which way is B? Is it into the page or out of the page? Into the page. So V cross B for the first particle. How do I do it? V is to the right. My palm is free to rotate. I rotate it so that I can close my fingers into the page. So the force on the first particle will be up. Great. So without any explanation, maybe I can just draw and nice. Have fun. How about the second particle? Let's again do the same thing. Minus 2Q. First, let's calculate V cross B. V is to the left. I have the freedom to rotate my hand. I rotate my hand so that I close my fingers onto the B, second vector, V cross B. So force, well, V cross B is down. The force is up. Why? Because I have a negative charge. So both forces were actually pointing directly upward. How many of you actually got this correctly? Come on guys, I expect better. Okay, good. So F1, F2. Draw the approximate trajectories of both particles indicating the direction of motion on the trajectory. So the first particle, the positive particle, does it rotate clockwise or counterclockwise? Counterclockwise. It's going to go around in a circle like this. Because I do not know the mass of the particle, the best I can draw is a circle. Okay, it may be a very small circle if the particle is very heavy, or it may be a large circle if the particle is light. Now, how about the second particle? Is it going to go clockwise or counterclockwise? Great. It's going to rotate clockwise. So that's actually a general principle. Positive and negative charged particles rotate in opposite senses under a magnetic field. Okay? And that's going to come into play today. That's going to be important today. Let's answer part C. The positive particle and negative particles have charge plus Q and minus 2Q respectively. What should be the ratio of their masses so that their motion has the same period? Now, I have already derived the cyclotron frequency. I remember it. You can derive it. It is QB over M, right? So to have the same period, what should I have? If the first particle has charge plus Q, the other has charge minus 2Q. Here, the important thing is, of course, it's always the frequency. I always can take it to be positive. The ratio of the masses should be, if plus Q particle has mass M, the 2Q particle should have mass 2M, because it's the Q over M ratio that matters, that actually determines what your cyclotron frequency or the period of the motion is. Okay? If I don't think many of you actually remember this cyclotron frequency formula, so what you could very quickly do is to say that the acceleration of this particle is towards the center. Acceleration magnitude will be V square over R, right? And that must be M times Q times VB, that's the force, MA. And from here, you could find V as MQ, not G, Q, B, R. And the period as 2 pi r divided by v, which is mqb r. I think I did something wrong here, because f is not, okay, a is not equal to m times f. A is equal to f divided by m. It's very good. So r's cancel, 2 pi m over qb, but the important thing is m over q ratio, which determines our motion. Actually, do you know how electron was discovered? The first elementary particle to be discovered. So, what a physicist, Thomson, did was he took a metal filament and he ran a lot of current through it. He didn't know what's carrying the current. He knew there is this object called electrical current. And that heat up this filament, that resistor if you want. And he observed that if he puts all of this in a vacuum chamber, so there is very little gas there, then some sort of ray is coming out of this filament. So he called this, because this is also called the negative terminal or cathode, he said there are cathode rays coming out. Right? Then he said, let's see if these cathode rays are charged. Okay? So what he did is, he actually put a metal plate here, so that most cathode rays are stopped, but only a small portion of them pass through the metal plates. Okay. And then he said, okay, if these are charged, maybe I can slow them down or even stop them. Okay. And he observed that if actually he gives enough voltage, he can stop these rays. He said, okay, so these look like whatever is carrying the current inside. Right? And then he did another experiment. He said, hey, let me take another capacitor and apply a voltage to it. So that will be plus charges here and minus charges here. Now my cathode ray comes in here. Now I know that it's made up of charged particles. What he observed is that instead of going on a straight trajectory, those rays actually bent. Why? Well, they are attracted by the electrical force, right? At each point, there is an electrical force. And why are they attracted to the plus terminal? Because they are negatively charged particles, right? So there is an electrical force on them. Then he said, oh, great. So maybe I can actually see how much they deflect. But that's a hard measurement to do, actually. The velocity, you have to know the velocity of these particles. And it's not very easy to know what the velocity of these particles are, right? So he said, he was a smart guy. He said, hey, what if I actually bring in some magnetic field? All right. So I'll bring in a magnetic field like this. Let me plot it with another color. I'll bring in a uniform magnetic field in this area. Right? Now, if the velocity of the particles is this way, and these are negatively charged particles, what's the direction of the velocity of the what's the direction of the force? V cross B is up. No, okay. V cross B is up, but these are negatively charged particles, so the magnetic force is down. So magnetic force is down. So he can't change how close his magnets are. He can't change the value of the magnetic field. He adjusted the value of the magnetic field so that there is no deflection. So magnetic force exactly cancels the electric force. Okay. Now why is that useful? Let's find out. How can magnetic force cancel the electric force? Well, what's the electrical force on the electron here? F electrical is going to be charge of the electron, which we are going to show as E, okay, times electric field, and that's, he knows the electric field because he designs the capacitor, okay. How about the magnetic force? It's going to be Q V cross B. If these two, for these two to cancel, well, I'm going to call this E again. For these two to be equal and opposite with a sign, so let me write it like this. E times E is going to be E times V times B. In other words, at the magnetic field, by adjusting the magnetic field, what are you measuring? You are measuring the velocity of the particles. So actually what you do is, if you put in a small hole here, all the particles getting out of that hole have exactly the specific velocity E divided by B. Right? And from that you can look at the deflection. If you measure the velocity of the particles, then you can actually measure charge divided by mass ratio of all these electrons, and that's how he actually determined the electric charge, well, electric charge over mass. And fortunately someone else actually measured electric charge separately, Millikan, and then they actually found that they have a particle with a specific value of charge and a specific value of mass. Right? Now whenever I talk about this experiment, a lot of freshman students have the same question. What about gravity? And why don't these electrons fall down? Why do you think I did not talk about gravity at all? Let's take a very modest electric field. Let's say 1 Newton per Coulomb electric field. It's not very hard to generate this. What's the electrical force on an electron in such a field? Q times E, right? So, do you remember the electron charge? What was the order of magnitude of the electron charge? 1.6 10 to minus 19 newtons here, if E is 1 Newton per Coulomb electric field. G is 10 meters per second square. What's the gravitational force on an electron on Earth's surface? M times G. Do you remember what's the electron mass? 9.1 10 to minus 31 kilograms. So with G, it's 10 to minus 30 Newton. So the gravitational force on an electron for typical electric fields in the lab is what? 10 to the 10 times smaller. 10 billion times smaller than electrical forces. So when you're thinking about elementary particles moving around, okay, under electric fields, magnetic fields, generally it's a good approximation to neglect that they are actually falling under gravity. Okay? Good. Now, we have actually looked at two formulas. Well, three. But what kind of magnetic forces did we learn about? We said for a single particle of charge Q, I have Q V cross B. If I have a current carrying wire, the force on that wire, it has this vector L, is I L cross B. And if I have a current loop, there was a magnetic moment which is I times the area, and there is a torque on this which is mu cross B. Now, I'll come back to the torque formula again. I'll go over it again. We were kind of rushing through that in the previous lecture. But let me go back to these two formulas. Are they the same thing or are they different things? Let's try to find out. Actually, Maxwell, the guy whose work we're more or less studying in this lecture, he was very, his mind was made up. He said the force, the magnetic force, does not act on the particles which are moving on the wire, but it acts on the wire itself. Okay. So he said these two formulas are two different things. Then someone noticed a very important property. And at that time, around 1860s, 1850s, I think, people did not know whether it was positively charged particles or negatively charged particles that are carrying current in a wire. And people said, hey, there is really no way that I can know whether positive particles are carrying current or negative particles are carrying current. Because if actually positive particles are carrying current, they are moving one way, and that will give me a net current I to the right. Or it might be just that, hey, maybe it's negatively charged particles. They are going the other way, which again will give me a current to the other side. There were some initial experiments trying to accelerate whatever the particles by real physical force. They said, okay, let's take a wire. I'm going to accelerate it very fast, so there will be a small current. If I detect this, I'll find out. It doesn't work, obviously. I mean, as we have just seen, electrical forces are much, much larger, billions times larger than what's comparable with gravity, or usual accelerations we have around ourselves. If you actually want to accelerate electrons so much that you can detect a current, you'll probably tear up the wire, you'll bend the wire, something terrible will happen, okay? You cannot apply that much acceleration. Now, here is the thing. This guy, whose name was Hall, he realized the following. He said, hey, what if I put the wire in a magnetic field? Let's say that magnetic field. Uniform magnetic field. Now, if let's say we don't know what's the truth. Let's say that I'm trying to send a particle, the first particle with velocity v through this wire. What will happen? Obviously, it will not stay on a straight line. Why? There will be Q V cross B force on it, V is to the right, magnetic field is coming out. So this particle will go towards the edge and it will probably sit there. Okay? If I keep sending more and more positive particles, all of them will add up. They will come to the edge. So what will happen? Because these particles went to the edge, they will actually create an electric field, right? And if they create enough electric field so as to cancel the magnetic force on the next incoming particle, then this guy can actually pass through without any problems, right? So application of a magnetic field, upwards magnetic field, will create an electric field perpendicular to the current direction. So the current is flowing to the right, but the electric field is upwards. So actually, if he takes a voltmeter and measures the voltage here, he will see that this terminal is plus and this terminal is minus. The lower part has more potential. Positive charges are stored there. But he said, hey, how about the other scenario? If I have negative charges flowing the other way, giving me the same current, and I have the same magnetic field, right? Now, which way is the force? V is towards me, cross B is up, so the force is down. Force is down because I have negative particles. Okay. So what happens to the negative particle? It goes to the edge. If I actually have enough negative particles here, they will create an electrical field towards themselves, which will repel this guy. So this F electrical and F magnetic will cancel each other, so that my electron can pass without rotating. So if I actually take a voltmeter, what would I see? I'll see the upper terminal is positive and the lower terminal is negative. So there is a difference. By applying a magnetic field, I can apparently find out whether it's negative charges which are carrying the current or positive charges which are carrying the current. And he exactly did that. He took a flattened, more or less flattened wire. Actually, he took a wire and beat it with a hammer to make it flat. He attached his voltmeter to the upper and lower terminals, ran a current under a magnetic field, and what did he find out? He found out that in metals, electrons which have negative charge carry the current. Now, Hall effect, this is called the Hall effect. Is extremely important. First of all, whenever you actually get a new piece of material that conducts, the first experiment you do is the Hall experiment. You actually want to determine the charge of the carriers inside, whether it's electrons or something else. And then, if you do this experiment more carefully, you can not only find out the positive or negative, you can actually find out the density of charge carriers, how many of them there are per unit area of that, or per unit volume. So it's a very good diagnostic method to see a new material. It turns out, in 1982, people created very pure samples, so there is no dirt in that, and put it in a very high magnetic field, and discovered something called the quantum Hall effect. And it's really remarkable. And this is a quantization of resistance. That's very interesting. Like, we know electric charge is quantized. It can be E2, E3, something like that. In this experiment, resistance is quantized. Well, its conductance is quantized, but nonetheless, it actually forms, there is a proposal, it forms the basis for some of the new SI units. Okay? Basically, it's a very, very precise measurements of electrons charge. And just a few years after that, and that got the Nobel Prize next year, more or less. A few years after that, people put even more pure samples into even higher magnetic fields. They discovered something called the fractional quantum Hall effect. And that's actually even more interesting from a theoretical standpoint, because in these new devices, these fractional quantum Hall effect devices, it worked as if electrons broke up into smaller particles, while they actually did not do that. They were still one electron. The behavior of the system was as if it's made up of particles of electron charge over 3, which is like quarks, right? So that was totally unexpected. It was very hard to explain. It was explained a few years afterward what's going on. But still, this is extremely, this whole experiment is extremely useful. And one more funny thing, actually, the samples they tried to create this fractional quantum Hall effect, it required new manufacturing technology to get very pure gallium arsenide, aluminum, gallium arsenide sandwiches, so-called. So this is late 1980s, and that technology pretty much made cellular phones, cheap cellular phones, possible. So if you're actually using these phones right now, if we can all afford cellular phones, the technology behind the chips inside these phones comes from the study of these fractional quantum Hall effects. So everything sort of comes in a cycle. Something starts as technology, ununderstood. I mean, people did not understand what electrons were. They just discovered there is something called battery and current runs out. Then someone discovers electrons. Then someone understands electrons are carrying the current. Then new effect is discovered and it comes back as cellular phones. So I find this fascinating. I think this is how technology and basic science work in hand, right? Now, as the last thing, let me go back to this torque on a current loop formula. And instead of calculating something, let me try to give you an intuitive picture of what's going on here. Let's just take a current loop in the xy plane. All right. And consider some scenarios here. First scenario. What if I apply a magnetic field in the z direction? A uniform magnetic field in the z direction. So B is B0 z hat. First things first, I have actually proved last time that if you have a loop, if the current is coming back onto itself, the net force was 0, right? There was no net force. But there may be a torque trying to rotate the loop. Now, if I apply a magnetic field in the z direction, is there a torque on this system? Let's try to look at the system from the top. If I look at the system from the top, right, let's say this is I'm looking at from the top, so this is my x-axis and this is my y-axis, and here is my current. For a small section here is my dl, and B, if I am looking at from the top, is coming towards me. So which way is the force? dl is like this, B is coming towards me, dl cross B, force is radially outward, right? So the force at that small section is radially outward. For all the small sections, the force will be radially outward. So what would this magnetic field do? Will it give a net force? No. Will it give a net torque? No. The only thing it does is it tries to actually expand the circle. If this was an elastic object, it will expand under the application of the magnetic field. What if I reverse the direction of the magnetic field? Would I get a torque? If I reverse the direction of the magnetic field, then all the forces would be inward. So it is trying to shrink the circle, but it's not trying to rotate it. Okay, good. But how about if I take the same system and apply a magnetic field, say, in the x direction? Now I'm again looking at the system from the top. So the top view would be, if this is x, this is y, here is my loop, it's rotating like this, and here is my magnetic field, be uniform. Now we must be careful. What's the force on a small section here, small dl here? It's 0, right? Why? Because dl is parallel to magnetic field. So the force on the other side is also 0. But how about the force on the small section here? dl cross B, let me do it again here. dl cross B is inside. So the force on that section is going to be inside. How about the top section? This way is my dl. Now dl cross B is coming towards me. Aha! So what does the magnetic field do now? It's pressing on one side and pulling on the other side. So it's actually trying to rotate it. Okay? So it's creating a torque. So it's basically trying to create a torque which would rotate positively along the y-axis. How did we show rotational quantities as vectors? If I have a pen that's rotating like this, how did I show its angular velocity as a vector? By the right-hand rule. If my fingers are rotating like this, the vector of rotation is perpendicular to the rotation frame, and it's determined by the right-hand rule. So which way is the torque here? I'll show that torque is in the positive y-axis. I'm going to write ijk. Okay. And here is my nice formula. If I want to actually find out the magnitude of the torque, the value of the torque, I don't actually have to go ahead and integrate all these small parts. I can do that, but the result will always be the same. Instead, I will define a new nice and thick vector. Okay, green. I will define the following vector. I will define a vector mu. What will be the magnitude of mu? It will be the current times the area of the loop. Okay. What will be the direction of the mu? Direction of the mu I will find out by right hand rule. I'll wrap my hand, right hand, along the direction of the current, and that will give me the direction of this mu. This mu vector is called magnetic dipole moment. Okay? And here is my nice formula. My torque is mu cross B. Let's check if mu cross B really gives me a torque like that. Mu is along the z-axis. B is along the x-axis. If I do mu cross B, my torque is really along the y-axis. Okay? So this formula is really nice, because otherwise, if you don't use it, if you don't define mu, and you'll actually have to calculate the torque for each small section and integrate over the loop. What I'm saying is, don't do that. Define your mu vector. It's simple to define if you know the area of the loop. Okay? So, although I did not prove this, I just actually calculated this for a rectangle. I trust Bilkent math department has already taught you enough calculus. If you can do it for a rectangle, by using calculus, you can actually do it for any arbitrary shape. Don't look so hopeless, come on. Practically, you just have to remember the formula, okay? But if you actually want to prove, I'm sure you can prove it using calculus, okay? So, torque on a loop would be mu cross B. Are there any questions about the definition of the magnetic field? How it applies a force on particles? How it applies a force on wires? Or how it applies torques on current loops? No? Yes? Okay, so this is actually a very nice question. The question is as follows. I did not study what happens if I let the wire go. I said there is a torque on it, right? So let's say that's my current loop. So my mu vector is like that. And now I'm applying a magnetic field like this. So mu cross B will be, torque will be this way. So I'm trying to rotate the loop like this. If I keep the magnetic field, what will happen? It's going to rotate. It will actually accelerate, it will rotate faster, and at some point, here will be my area vector, mu vector, and magnetic field is like this. So mu cross B will be 0. But it got some velocity, so it will keep rotating. Now what will happen? Mu cross B. Now the torque is in the other direction, so it will slow down and then rotate back. So this is going to, if I just leave the system under a magnetic field, it's going to oscillate. Okay? So how do, and I'm getting ahead of myself, but what happens? How do you actually keep turning a current loop? You either oscillate your magnetic field or rotate your magnetic field, or you apply alternating current onto your loop so that it keeps rotating. Okay? Very good question. Any other questions? Yes?
If we apply this and turn it, we get an alternative.
Okay, that's a different issue. Okay, I'm just talking about the forces. I'm saying if I apply alternating current to the loop under a constant magnetic field, I can make it to rotate, go faster and faster. That's what I'm saying. Okay. The other way we'll talk about when we talk about induction. So pretty much in 2 weeks. Okay. So that's all I want to tell for today. I'll see you hopefully on Monday. All right.